Yeah.
He logged me in. That's very cool.
Okay, I am streaming. Okay, I double checked that it's recording my desktop audio, or at least the sound bar was dancing. Hopefully it doesn't get too fucked up. Okay. Okay, I got Discord.
This little St. James?
Yes, little St. James.
He doesn't have the voice channel showing.
Oh, because you probably forgot to give you permission to join. Let me. That's a good catch. Oh boy, how do I get that? Fuck.
Permissions, I think. No.
Oh, yep. Here we go. And lecture enjoyer.
Nice.
There we go. Ooh, that's a good catch.
What's this? Kitchen thingy.
Kitchen, that's the... Okay, perfect.
You want a camera test if I'm going to be in frame?
Yeah, well, so OBS stole the camera.
Okay.
So one idea I had was that Mike could put his webcam up, and then people could see our face, but it's...
Seems like it's
Well, we
not
can
your
use the
priority.
cam on this laptop.
Yeah, that was my idea, because OBS has stolen the camera over here.
Okay. Stream failed to start.
Just do close stream and try again. Probably. Try that.
Well, yeah, I could put this like this if you want.
Yeah, that was my idea, is turn the camera on, and then anyone who joins can see what we can
So
see.
your screen share to date has not worked for him.
Oh my god. Okay, let's all get out of the call. Okay, this is a common issue with Discord. Okay, everyone get out of the call. Okay.
Now, do you know that there are settings on screen share?
Settings where?
Hit the green screen share.
Where?
Sorry,
nope.
not that. Yeah, so you share again, not the stop streaming, but the little down arrow next to it. And more options. Now, oh shit. Change screen?
That'd be if I just wanted to change the window, but I do want to
There are some interesting settings that I might want to explain to you. There's Discord has a notion of text readability versus smooth motion. Smooth motion is for gaming.
Oh, I think that those only exist if you have the quote native app installed.
Might be.
And I don't want to install the native app, so. Okay. Mike, can you try joining the kitchen again? Let's see. We might be overloading my mom's pour. Okay. So, can you... Here, I can just mute you.
Should I mute myself?
Or I think I muted you.
Yeah, I already muted.
Okay, it's good. Yep.
You want him to try to hit watch stream?
Yeah, try hitting watch stream. Let's make sure that works.
Mike, do you have Xfinity as your home internet provider?
No, I have a fiber thing.
No worries.
So I can't. You mean tie into an Xfinity account?
Yeah.
I don't know. Okay, if it does... Jesus Christ. Hopefully,
You
if
might
it...
be able to just look at your screen.
Yeah, Mike, you're going to be able to see this, right?
I could connect to my own Wi-Fi for this if you want me to. You think that might be an issue?
His hotspot.
Hit close stream. Okay. Do me a favor.
Or I could install the app.
Click the little camera button at the bottom. Okay, I just want... Come on.
I see you.
Oh, for fuck's sake. Isn't Discord terrific?
Yeah, his hotspot is not a terrible idea. Also, I don't know if the native app...
Well, your mom's internet is fast. Look at this thing. 411 with 201 upload.
Yeah,
That's like
it's...
plenty.
Okay. I don't know what the issue is. Let's if it doesn't...
It's something with your laptop.
Okay. You think it's an issue with my laptop?
It might be.
Okay, I don't know.
We'll install the whole Discord on it.
I'm not gonna
Which
do...
is fast. I mean, it installs fast.
It's fine. When was the last time you screen shared with this setup?
Yesterday.
You want X or Wayland?
X.
Okay.
Well, unless Ubuntu changed it to Wayland under my, I'm not gonna upgrade Ubuntu
I'm
again.
not going to change it. I can tell you which one you are if you go to terminal.
Come on. Oh wow, it's slow.
You do echo, and then it's a certain environment variable. It's something underscore session type.
I don't know. Here.
Do env, yeah.
Let's just see if I have Wayland installed. Why is it so slow? Okay, Wayland, it's X Wayland. I have
So
installed.
Wayland, yeah. I think it's echo xdg underscore session underscore type.
Okay.
Puppy doggies.
No, it's X11. Okay. I don't know. Okay, so 720p is like eating all of my CPU.
Huh.
We'll have to.
Do you want to use this one?
No, here let's. I don't know. Okay, you're still cameraing. Okay, we'll try. We'll try it. We'll try going. Okay, this only matters if people join and they can't fucking see, and so I don't know.
You could send them a link to your slides and have them pull it up.
Yeah, I put the PDF. Yeah. Oh, for fuck's sake! Look at this.
You could just say, and now we're going to page 3, and now we're going to page 4.
Okay. All right. Let's get started. All right. Okay. All right. Hello. I am Peter Harpending. I work at QPQ. These are a couple of my friends. All right. Let's get started. So, what I am explaining is the starting point here is this problem that I call the lying knights problem. So, there are 3 roads in front of you. They're called the Golden Road, the Marble Road, and the Stone Road. And down exactly one of these roads is the Holy Grail. So, there's a knight in front of each road, and this is what the knights say. This road leads to the Grail. This is what the knight of the Golden Road says. Dude, I spent like an hour trying to get ChatGPT to generate this. And
that's awesome.
Well, dude, I tried like 5 different models, and ChatGPT was the only one that would actually generate it with the correct number of knights and roads. Grok had like a random knight sitting over here.
So do I find these slides here in another channel?
Yeah, they're in lectures. It's towards the bottom. It's a PDF file.
Oh, gotcha. Okay.
There you go. There you go.
Okay. Maybe it will open. Nothing wants to work at your place.
Yeah, I think I don't know what the hell's going on. Anyway, so the Knight of the Golden Road, what does he say? He says, Mike, is that big enough for you to read?
Yeah.
Okay.
I can't see that far, but yeah.
You can't see it. It's like 2 feet away, dude.
I know.
Nearsighted.
I need glasses.
You need glasses. Okay.
Oh, wait, it's opening.
Dude, you drove here.
All right.
Okay.
Cool. I see it.
If you open it in like a proper PDF viewer and hit presentation mode.
Or Control Plus.
I don't have
'Cause-
one.
Okay.
All right.
So, Knight of the Golden Road says, this road leads to the Grail. Also, if the stones take you there, so does the Marble Road. The Knight of the Marble... Here, I'll just fill them all in. The Knight of the Marble Road says the Gold Road, the Marble Road, and the Stone Road. The Knight of the Marble Road says, neither the Gold nor Stone roads lead to the Grail. And the Knight of the Stone Road says, follow the Gold and you'll reach the Grail, follow the Marble and you'll be lost. Okay? So, the problem is, all 3 knights are liars, and exactly one of those roads leads to the Grail, and the question is which one? So this is like a problem...
Well, if they're liars, does that mean they lie all the time, or do they lie sometime? Because if they lie all the time, then you can...
So
might as well they could be telling the truth, because you're going to reverse whatever they say.
Just assume that if you take the conjunction of both of their statements. So, like, each of the knights said two things. That's a good question. So, the Knight of the Golden Road said, this road leads to the Grail, and another statement. So, each of these knights said two things, and so assume the conjunction of both of those things. So, like, this knight says, this road leads to the Grail, so the gold road leads to the Grail, and if the stones take you there, then the marble road takes you there. So, it's called De Morgan's Law. So there's two statements here, and the and of the two statements is false, which means at least one of those is true, if that makes sense.
Yeah.
Okay.
Gotcha.
So, everyone guess?
It's a stone road, of course, that takes you there.
What? Really? Why do you say that?
Because that's the one that takes you to the Holy Grail.
Is that some movie I'm not familiar with, or?
No, it's just from what they're saying, right?
How did you figure that out? Or did you fucking scroll to the end?
No, I didn't scroll anywhere. I was here.
So I'm curious. How did you just? What was your?
Because the golden guy is a liar, but he also says if the stones take you there, so does the marble road. But then the next guy basically tells you that the stone one is the one that takes you there, because he says neither the gold or the stone leads to the Grail, implying that his marble road will take you there, which is not true. But also the other guy said that his gold road will take you there, and he's a liar, therefore the stone has to take you there.
Okay, that's interesting. Okay.
Right?
So I'm going to record everyone's guesses.
I just scrolled to the end.
I don't think...
It's so funny. What the heck, man?
So... Okay, Alex, what was your guess before?
I haven't worked it out. Stone?
Okay.
But yeah, he's sitting on the gold road, right? And he's like...
Yeah,
this will take you there. But also he says if the stone takes you there, the other one takes you there. And then the second one basically tells you the truth, because he's like... neither the gold or the stone goes there.
Okay.
Implying that
Either
his
gold
goes
or
there.
stone.
So both two are liars. The other guy didn't even have a chance to speak.
Okay. Interesting.
I don't know what the stone guy said. What did the stone guy say?
Follow the gold and you'll reach the Grail. Follow the marble and you'll be lost.
Interesting.
Okay. So anyway, Mike has generously agreed to pay a $50 prize to be split among all those who agree.
What the hell? He's on the gold trail right now.
Among all those who guess the right answer.
He's the knight on the gold trail right now, talking to you guys.
All right. Yeah. Well, I have it in writing, Mike. So.
No, I see. See, there you go. That's how many statements did the golden guy make? Oh, he did make two statements. See,
yeah.
You're on the gold path.
Okay, so the goal here is to solve this problem, and Mike figured out some way to get to it. I don't actually remember what the correct answer is. I think it's the stone road, but I don't actually remember. I did make sure the demo worked, and I don't remember what the actual answer is, though. Okay, so the goal is, by the end of this lecture, you'll have some sort of systematic way to solve this problem.
Okay.
And basically what I'm showing you is sort of a more elegant version of Boolean algebra that you may have learned. Both of you have had some programming experience, right? Mm-hmm. Okay, so you've dealt with Boolean algebra via like if statements, right? Mm-hmm. Okay.
Is it the Chinese remainder theorem?
No. I at one point knew what the Chinese remainder... I mean, I know I could go look that up, but no, this is a much more basic thing than any of that. So I'm sure the Chinese remainder theorem is related to this, though. Anyway, so the goal is I'm going to show you kind of a way to deal with complicated logical statements where you can sort of prove that something is the correct answer without having to think about it. And even if, somebody in the audience is a professional mathematician, this will be new information. So Ground rules. Mike, you gotta start drinking. I don't give a shit about driving or any of that stupid thing. 2 drink minimum. All right. So
Why?
why? Because I said so.
Bro, I don't need to drink to act like I'm drunk.
That's a good point.
know me.
Yeah, that's a good point. Okay, you're Eastern European. It's just kind of like your DNA.
It's my default state.
Yeah, your DNA just produces. You're resting.
Self-internalized alcohol.
Exemption.
Oh yeah, he's Muslim.
My
That's right.
liver produces alcohol, so
Yeah.
I'm good. It's the reverse liver.
Yeah. Anyway, so have fun, learn some stuff.
I synthesize.
If you have questions, please interrupt.
Okay.
Let's try to minimize the distractions, Mike.
All right. That's gonna be a challenge.
Yeah, I know. That's we don't need to self-censor.
How did this appear here? Mike has generously agreed to bankroll. You just said that to me in words.
Yeah, and I have it in writing.
Oh, that's what you. That's like, what the hell? Where does that come from? It's like
Yeah.
it appeared here after you said it.
Yeah, because you're a couple slides behind. That's why.
Okay.
Yeah, and
Okay.
anyway, I hate editing videos. Please don't make me edit the video, Mike.
No, I won't.
Okay. So I told you guys that this was about cryptocurrency, and so why the hell are we talking about logic? Logic is obviously important, but specifically the way that this thing works makes heavy use of modular arithmetic.
What's WF algebra?
That's what I'm explaining.
Okay.
That's what the talk is about.
Oh.
So modular arithmetic is very, very important in cryptography. It's kind of the whole thing.
You got a piece of paper.
So now he wants a piece of paper.
Yeah, because you said you can solve this with math.
Yeah. I'm going to show you how.
Got it.
That's the point.
Okay, got it.
Right, yes, zero knowledge proofs like Zcash.
Yes. So more sophisticated versions of these ideas are kind of central in cutting edge cryptography, and it's really interesting. And I also have some original work here, which we'll get to at the end. Disclaimer, the guy who came up with this way of thinking about Boolean algebra is a guy named Norman Wildberger. Most stolen from here. Yeah, I do have an original contribution. We can probably talk about it at the end. I'm going to show it to you. That's what the demo is. And then we'll get to the end. So
It's George Boole.
yeah, that's George Boole. So Booleans are the values true and false. So, and Boolean algebra is basically just, all the rules about how to manipulate the values true and false. Specifically, when people talk about Boolean algebra, though, they mean sort of this version that uses 3 basic operations: inclusive or, and not. And so all we're doing, Wildberger, he calls this algebra of Boole, because actually Boole's original formulation of this used exclusive or as the or primitive instead of inclusive or. And what we're going to see is that when you use exclusive or instead, it's actually much cleaner. It's less maybe. A lot of the stuff with Wildberger is a very, very interesting heterodox mathematician. He developed a version of trigonometry that doesn't require angles.
His name is Wildberger.
Yes.
Okay.
He's Canadian, and he lives in Australia.
And he did math.
Yeah, he's a math professor at the University of New South Wales. He might be retired. Anyway, he's a very weird heterodox mathematician. He believes that most of mainstream mathematics is actually wrong.
Oh, Wildberger, not burger. Burger.
Yeah, Berger.
Okay, I was thinking burger.
Okay, yeah. So actually, Boole's original formulation of Boolean algebra used exclusive or instead of inclusive or.
Mm-hmm.
Okay, so this is the usual version. So typically, the way that this is explained to people, if you take like a basic course in logic or your first pure math course, is it's going to be explained in terms of these Venn diagrams. So inclusive OR, the set theory version of that is called the union. So A union B, let's see. So X inclusive OR Y, that is true if at least one of X and Y is true. So if both of them are true, then A inclusive OR B is true. I don't know what page number we're on. We're on the usual story, Mike, if you're following.
Okay. I don't know. Oh, wildberger. Yeah.
Okay.
What page is that?
I don't know what page number it is. Keep going. Keep going.
This one.
No, no.
It's this one, but every time he advances the bullets, it's going to be still the usual story.
There we
Okay.
go. Okay. Yeah. Sorry. So the way it works is that if I want text to appear, it in the PDF that becomes a new
that's
page.
Why I was like, why are you repeating things so much?
Yeah, it's just because like in presentation mode, I hit next, it goes to the next
I
page.
think F5 is.
Yeah, hit F5. Try that.
It doesn't work in browser. Okay.
Yeah, you might need to open like it with the system PDF viewer.
Holy cow, we're on camera, dude.
Yes,
Can people see this?
if they are in the Discord.
Okay. Let me know if I'm picking my nose or something.
All right. Okay, and try hitting F5.
It didn't work. It put me nowhere.
Okay, we're on the usual story.
Yeah. Right?
The one with the blobs.
Okay.
Yeah, there we
This
go.
is like Aristotelian syllogisms.
Yeah, Aristotelian. Yes, exactly. Yeah. So Wildberger, if you want to learn math from some like a historical point of view, that's kind of very much his thing, is kind of going back to, Euclid, Archimedes, Aristotle, the, really great Greek mathematicians, and saying, okay, knowing what we know now about, especially about algebra, which is a tool that they just didn't have. Okay, what is like the correct version of Euclid? And what about Euclid is kind of clunky and awkward? How can we kind of make this better? And it's a really, really interesting thing. He developed a version of trigonometry that's entirely algebraic, so there's no transcendental functions, there's no angles, everything is just polynomial identities. It's really, really interesting. It generalizes a lot better. It's much less like visually intuitive, but like it's a lot, it's much cleaner. And this is kind of a similar thing. It's a little bit less intuitive, but like in terms of how it works, it's much cleaner. So 3 basic primitives in the usual version of Boolean algebra are inclusive OR, and not. So inclusive OR, X inclusive OR Y, is true if at least one of X and Y is true. Does that make sense? So if both X and Y are true, then A inclusive OR B is true. X and Y, which is also called the intersection, if you're talking about sets, this is true if both of X and Y are true, otherwise it's false. So the So not X is true when X is false, and vice versa. So in math, in set theory, this is called the complement. So the A complement, which the normal notation is A superscript C, it's the set of all X such that X is not in A. Does that make sense?
A to the power of C.
Yeah, scroll down a couple things, pages. Just hit page down every time to get to the next slide.
Oh, yeah, I don't have a page down. Okay.
Yeah. Okay. So.
Too far.
Okay. Our version. Sorry, Mike. I should have picked a bigger do you maybe want to switch places with Alex, and then that way?
No, I'm okay.
Okay. Cool.
I'm good.
All right. So our version of the story, we have XOR and not. Let me just. Oops. So X exclusive OR Y is true when exactly one of X and Y is true. Otherwise, it's false.
It's not an exponent. It's a curve, an upside down curve. It's not an exponent.
Well, a complement is usually an exponent.
Okay.
Yeah, so that's the way you pronounce that. It's math notation is really fucking stupid.
Okay.
Yeah, so we're talking about So
Yeah, so it's kind of what I said. The two guys kind of gave away the stone part. But I did that in my head.
Okay, yeah. Mike is bizarre because, like, sometimes he'll just, like, make these crazy logical deductions out of thin air, and it's like, how the fuck did you do that? Right. And then, like, you try to explain some, like, really basic thing to him, and he just doesn't get it.
That's called a halal math.
Halal math.
Halal math. There you go. Bizarre math, bro. Straight smarts math.
It was pretty impressive how, like, fast you did the logical deduction. Do you want some more? You want some more liquor? No, what the hell's your name, Alex?
I'll grab it.
Yeah, if you want some, there's here. Then. Okay, and then intersection and complement are the same. So another way to express these is in terms of these so-called truth tables. So.
Oh, it's down there?
Yeah.
Okay.
Yeah. So, Mike, this should be big enough that you could see it on my screen. Mike, how did you drive here? Don't you have glasses?
I have sunglasses.
Oh, okay.
Yeah, the prescription.
Okay.
Mm-hmm. I lost my clear once, so I don't know. We'll see.
Okay. So you're gonna drive. Okay, you're gonna drive home with sunglasses.
But see, look at this. This is similar to what I did, but in a different notation, in my own way.
Okay, I'm very curious to
You
see how that
Yeah, same. I got my annotation.
Yeah.
Okay, Chinese remainder. I would have to think about how.
Well, it's a modular thing, so we'll talk about it later.
Yeah, Chinese remainder thing.
It's
I mean, that's
basically
like,
Before we got to this, he says the gold one, yes, will lead you there, but it's false.
It's basically like a systems of equations as a matrix, but for modular.
yeah, it's about.
And then you do the echelon reduced form or whatever.
Yeah, so I think the Chinese remainder theorem, if I remember correctly, I remember when I took like a cryptography class. But I think what it is that
really nicer.
It's that if you have if you have fuck, what the hell's it called?
The determinant.
No. If you have modular equations in like different moduli.
Yeah, exactly.
Then like there's a unique solution.
Yeah, you take the LCM of all the
modulo the
or something.
LCM. Yeah, I remember that, and it's a really fundamental theorem in number theory. I just don't remember exactly what it is.
Yeah, now that you said that wildberger is into modular stuff.
Yeah. Well, we'll get into it. So, two very, very important concepts that I just laundered in. Number one is, what are you doing, Mike?
Oh, I got distracted by Discord on the phone.
Yeah, okay. So, number one is this idea of... All right, well, we'll see. He's getting distracted.
I'm good. I'm listening.
Okay. Number one is this concept of using 0 to represent true, false, and 1 to represent true. Does that make sense?
Yes.
Mm-hmm. All right. And then thinking of truth tables. So that's this idea of, if A is true and B is false, blah, blah, blah. Thinking of those as functions.
Well, what's LIOR function?
That logical inclusive OR.
Okay.
That's what that stands for.
L and?
Logical and then L not, logical not. That's what the L means.
Oh, so the first one is the intersection of both?
Yeah, so it's
the second one is the second one is intersection. The other one is both together.
Yeah, that's called union.
Intersection.
Yeah.
And complement.
That's like exclusive.
It's like not. It's like
it's negation.
Negating.
Yeah, so A complement, that's how you read A to the C, is the set of all elements in the universe that are not in
It's
A.
like an exclamation point A in program.
Oh, so it's everything but A.
Yes, that's what.
Invert A.
But why do you care about the whole rest of the universe and you exclude A?
There's many situations in math.
Oh, so you
where
can say like possibilities, right? Like all the roads in the world will not. lead
That's what
to
the
the
universe
holy
is.
grail.
Yeah.
It's possibilities.
Yeah, so okay, I'm not going to get into a diversion. If you want to understand why, like I wrote it as universe minus A, look up something called Russell's paradox.
Okay.
Okay.
Cool.
So it's there's a version of it called the barbershop paradox. It's maybe easier to understand. So Mike, so let's what's the way to think about it? All right, I just got to think for a quick second. So okay, so let's say that we're in a we're in like a small town. So we're in like the city I live in undisclosed location. There's one barber in the entire town. Mm-hmm. Okay, the barber cuts everyone's hair who does not cut their own hair.
Okay.
Okay. Does the barber cut his own hair? And it turns out there's a contradiction there. So let me.
Depends on the barber.
Well,
or what kind of haircut he likes. Because if he buzzes, he might just buzz his own. So not give a crap.
Well, okay. See, this is the thing. This is what I was saying. Is that like
right?
He can just do these crazy logical deductions incredibly, and then I explain something like really basic, and he goes, "Well, does he like a buzz cut or not?" And it's like, no, that's not the fucking point, Mike. Okay, here, Jesus Christ. How do
well, the question was, does he cut his own hair, right?
Yeah, but it's not actually about his hair, you chimp. Okay, so this is the math version of the problem. So we're thinking about all the sets X such that X is not an element of X, okay? And we're just going to call this set A, okay?
Well, how is X not an element of X? Is there a different X?
People who
Hey, get off the counter!
People who don't cut their own hair.
So this is all the people in the
why are they not marked as something else, though? Why don't they have a property? Because people that cut their own hair are different than the people that don't cut their own hair. Right?
What is your... I don't understand your question.
So why would you write it like this where it's confusing? They're both X when they're not the same thing.
Okay, so...
Because, no, this is what I'm saying. Like, okay, so people are X, let's say.
Okay,
people that cut their own hair versus people that don't cut their own hair, they're an X, Y, and XZ, right?
Okay, here.
So XY plus XZ is X.
Okay, barbers, customers.
Uh-huh.
Okay, this is equal to the set of all, citizens.
Everybody. What's that?
Citizens.
Citizens.
Okay, perfect.
Such that, the citizen does not cut their own hair.
Yes, okay, yeah, that makes sense. Yeah, because otherwise they wouldn't be in his shop. Right? Yeah.
And I shouldn't have said customers, I should say barbers, let's just call them victims. But anyone who is the barber's victims, but by victim I mean the barber cuts their hair. That's what I mean. Mm-hmm. Okay, and so this is the set of all citizens that do not cut their own hair. Does that make sense? So...
However, there are some that they could have their wives cut their hair.
Jesus Christ!
And they don't have to.
No. That's so. This town is some weird cult.
Okay.
Where
only he can cut their hair.
Either the barber cuts their hair, or you cut your own hair.
Gotcha.
Your
Perfect.
wife can't cut your hair for you. Okay. It's some weird fucking. Okay,
right.
This is math.
Makes
all right.
okay.
Logic doesn't apply.
Okay. Gotcha.
Okay. The problem is the barber in the set of people in okay, does the barber cut his own hair is the question.
He's not in that set. No, he's not.
Well, here's the problem. If you say the barber does not cut his own hair, then definitionally he is in this collection. Because this collection is all the people in the town who do not cut their own hair.
But
that
collection is barbers' victims.
Yeah, but the collection is defined by him, so he's like a god.
No. It's not defined by the barber.
He's the god of that collection.
No.
Well, he's not part of the collection, though, because he's the one that defines the collection.
No, the barber doesn't define the collection. The collection is defined by God, and the barber is not.
But if he refuses one customer, then he's not part of that collection, so that makes him the god of this parenthesis thing. Right?
It's the whole math. Either way you pick it, there's going to be a contradiction.
So here's the thing. Okay. Stop thinking about like an actual barber.
Okay.
All right. This is just meant to be illustrative. Okay. if the barber cuts his own hair, then definitionally he is not in the collection of people who are the barber's customers. Or he's not. So the barber cuts everyone's hair as long as they don't cut their own hair. Does that make sense? Mm-hmm. So if you don't cut your hair, then the barber cuts your hair.
Yeah.
And if you do cut your own hair, then the barber doesn't cut your hair.
Yeah, he's eliminated.
Okay. The problem is that what happens when you apply that logic to the barber?
He can be both.
Right. So the problem is that you get a circular logic. You get a circular thing.
You get an impossible contradiction in either case.
Right. So if the barber cuts his own hair, then he's excluded from the people whose hair is cut by the barber, because the definition is the barber cuts everyone's hair if they don't cut their own hair. But if the barber cuts his own hair, then he's excluded from that set. Does that make sense? Mm-hmm. Okay, but so we can say, okay, the barber doesn't cut his own hair then. But then, definitionally, the barber cuts that person's hair, so therefore the barber cuts his own hair.
Yeah, so he's a special case.
Yes, that's the point. That's the whole point. This is called Russell's paradox.
Yeah, he's a special case, so he's got more properties than the rest of the...
Yes. So this is a problem in math with if you are not careful with how you talk about sets.
So we have to annotate the barber in a different way, so we identify him. So
basically the way that you avoid running into Russell's paradox is that you have to explicitly specify that there is some sort of universe. That's how you avoid getting trapped by things like Russell's paradox. So that is why I said a complement is there is some universe. Subtract A.
Okay, so there's outside of this.
Right. We have defined the scope of all possible things.
So does that make it the barber, the universe? Is he part of the universe? Is that why we're doing this? Because he's not part of the set. He might have
I don't know how to answer that question.
He might have a relation to that set, but he's a special case.
So
Might want to edit this all out.
No, this is good. I don't know how to answer that question.
Okay.
So I'm just not going to.
That's okay.
Okay. So what's the problem with this? Well, nothing. Boolean algebra works. It does run the modern world. Because this is the way that Boolean algebra works in software, in every programming language, and software runs the world. It's just kind of ugly. And like by analogy, if you think about heliocentrism versus geocentrism, okay, both of these are equally consistent models of planetary motion. Neither one is strictly speaking wrong. So the model on the right is very complicated, and it has a billion different curves, and there's not really necessarily an obvious causation.
The corrective factors are called epicycles.
Yeah, epicycles, right. We're actually probably not in this lecture, but anyway. So the analogy is that heliocentrism is just simpler. It's not necessarily that it's more correct, but that it's simpler. So, yeah, right. So geocentrism isn't wrong in any strict sense. They're equally consistent models of planetary motion. It's just like, no. Like, it's very complicated. So, our setup here is mod 2 arithmetic. So we're on mod 2 arithmetic setup.
Okay. You have a lot of blank pages. Okay.
Okay. So 0 in mod 2 arithmetic, red number 0, it's the set of all even integers. So 0, plus or minus 2, plus or minus 4, etc.
Is that why it's called mod 2?
Yes. So mod...
Like anything that's 2 to the power of n, whatever.
Yeah, so
2, 4, 6, 8.
Yeah,
2 times n, such that n is an integer.
Okay, let me give you an example that you are already familiar with. So right now it is 6:18. What time is it going to be in 12 hours?
6:18 in the morning.
Right, okay. So that is mod 12 arithmetic.
Okay.
Is that that 12 is equal to 0. So you add 12 and it doesn't change the time.
Okay.
Yeah. So all we're doing is mod 2 arithmetic. So it's like the simplest possible version of that.
Okay.
So in cryptography, we do mod p arithmetic, where p is a prime number.
Mod P arithmetic.
Where p is a prime number.
And that number can be as long as you want it to be, or?
Yeah, they're typically really, really, really big prime numbers. And the reason you do that is because, okay, I wrote about this in an article, but essentially, so if we do mod 5 arithmetic, it's the case that, okay, here, mod 5. So if we take 4 times 4, what is 4 times 4 in mod 5?
In mod 5?
16 mod 5.
No,
10,
so it'd be 5
15.
times itself 4 times.
No.
So
4 times 4 is what?
16.
16. And so in mod 5 arithmetic, that means that you subtract multiples of 5.
5, 10, 15, it's 1.
It's 1 in mod 5 arithmetic.
Because it's 1 off of 15, which is...
Yeah, it's one off of, it's a multiple of 5 plus 1. Does that make sense? So look here. See how it's, so 0 is the set of all integers that are 2 times n plus 0 in mod 2 arithmetic.
Okay, wait. So mod 5 is 1 because...
Okay.
Why is 16 mod 5 1?
Because
You eliminate all the 5s out of it?
No, because you have a clock with 5 tick marks. You go
Okay.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and you go
So
around.
17 would be 2?
Yes.
17 would be 2,
Because it's a
18
clock
would
with
be
5 tick
3,
marks. Yeah.
Okay.
18 would be 3, 19 would be 4.
So 19 mod 6 would be 1.
Correct. Yes, exactly.
Yeah, the mod is how many tick marks on the clock.
The mod is how many hours there are on the
5,
clock.
mod 12.
They eliminate themselves.
Correct. Yeah. So when you get to whatever the modulus is, then that is 0.
So if you have mod prime number, if you have a number that's that prime number plus...
Yes.
If you have a number that's that prime number times 20,000 plus 5, it would be 5.
Yes. Correct.
Basically.
Yes.
It doesn't matter if the number is like into billions.
Correct.
Okay.
Yes. Yes.
Gotcha.
Okay. The reason that we pick prime numbers, let's just pick 5. 5 is a very small prime number. Mm-hmm. So I was saying 4 times 4 is what? 16.
Mm-hmm. Oh, so you don't confuse it with other mods. Because 4, you could say it's a mod of 2.
Not quite. Let me get through this. Let me explain. So 4 times 4 is 16, which is 1 mod 5, right?
Yeah.
Okay. 3 times, let me just do it in my head. 3 times 2, that is what?
6.
6, which mod 5 is what?
1.
1. Okay, cool. 2 times 3 is what?
I don't know, 6.
6, which is what, mod 5?
1.
1. Okay, and then 1 times 1 is what?
1.
Is 1, which is 1 mod 5. So, in mod 5 arithmetic, every number there's another number, mod 5, such that when you multiply x times y, you get 1. So here, I wrote it down here. So 4 times 4 is 16.
Yeah.
3 times 2 is 1. So every number in mod p arithmetic, you can always get back to 1. There's always some way to multiply by something else to get back to 1. Which is the same thing mathematically as there being division.
Okay.
Right? The exception is 5, because 5 is equivalent to 0, and there's nothing you can multiply 5 by where you're going to be 1 off from a multiple of 5.
Because there's no division by 0.
Right. It's the same reason there's no division by 0. So 5 times 2 is what?
10. So yeah,
10.
Anything that's
Yeah.
5 will be...
Right. You can never get
Yeah.
to a multiple of... You can never get 1 off from a multiple of 5 by taking 5 plus itself a bunch of times. You're always going to get a multiple of 5 plus 0. Okay. Let's instead talk about mod 12 arithmetic. The problem with mod 12 arithmetic, 12 is a composite number. So if you take multiples of 3, let's look at multiples of 3 mod 12. We get 3, 6, 9, 12. And then it'd be 15, which is back to 3.
So in mod
6.
3, 12 would be nothing.
Yes, in mod 3, 12
Because
is equal
3 is a factor of 12.
Yeah, so in mod 3, 12 is equal
Same
to
with
0.
mod 4 and same with mod 2.
And
Yes,
6 as well.
correct.
Yeah.
So what I'm talking about, though, is let's suppose we're in mod 12. We're talking about mod 12.
Okay.
Okay, and we look at 3, and we want to compute what is the multiplicative inverse of 3, which means I want another number, mod 12, such that when I multiply that number by 3, I get 1, mod 12. And the problem is that you look at the multiples of 3, it's 3, 6, 9, 12. Then you look back, 3, 6, 9, 12. 3, 6, 9, 12. The problem is that it's a cycle, and you never get to 1. Whereas if
What do you mean? 13
Because
is,
it's a factor of 12.
13 is the mod 1 of 12.
correct, but 13 isn't a multiple of 3. There's nothing you can multiply 3 by to get to 13.
Oh.
So
What about 25? That's a mod 1 of 12.
Yes. My point is that if you have a composite modulus, so if you have a modulus that isn't prime, there are going to be some numbers that don't have multiplicative inverses.
All right, so like 12, because 3 is a factor, we have a special case 3 doesn't work.
Does that make sense? But 5 mod 12 does have a multiplicative inverse, which you found, which was 25. So 5 times 5 is equal to 25, which mod 12 is equal to 1.
So factors of the modulus break it. So that's why we want a modulus with no factors, aka a prime modulus.
Does that make sense? If you have a prime
On the light on?
yeah, that's probably a good idea.
Yeah, I didn't know that's why you wanted a prime one.
Yeah, that's why you want a prime. Whoa, that's way too bright.
That's good.
But that's why you want a prime modulus, is so that every number has a multiplicative inverse. Does that make sense?
Yeah.
Okay.
Are there other people in here?
The Canadian guy said he'd be around in a couple hours, and then maybe the guy from Japan will join, but
Okay.
we'll see. I mean, it's like 8 in the morning in Japan, so,
Oh yeah, that would be.
and it's on Monday, so, and he actually gets work done, so.
Ohayou gozaimasu.
So right, for now, fuck. For now, it's just us. So that's why you want a prime mod. That's why mod prime number is super important in cryptography.
Okay.
Is because if you are working in modulo a prime number, then you can do division. But if you have a composite modulus, you can't it's not necessarily true that every number has a multiplicative inverse.
Breaks.
So how do they pick this prime number? Arbitrarily or?
Well, the NSA, basically every cryptography scheme is published by the NSA, and the NSA does not disclose, they will pick the prime number as part of the definition of the cryptography scheme.
Wait, so you have to use something that NSA provides to you?
Correct. So all of your cryptocurrency, all your Bitcoin, all your Ethereum, all that shit, the trust model at the end of the day is we are going to blindly trust that the NSA was not doing anything weird with these
So why
cryptography schemes.
are we not using our own stuff?
Because the NSA says that it's wrong.
And then you're not allowed to?
No, you're allowed to. It's just the people who write cryptography schemes are retarded and just blindly trust the NSA.
Gotcha.
Okay?
Gotcha.
No, it's some weird cargo cult thing. It's like, well, the NSA would never lie to us.
I see. Okay, so they take that as like God-given.
Yeah, the NSA is an all-knowing, all-powerful entity that is a universal force for good, and they would never do anything nefarious.
So this scheme, I'm imagining this scheme has other things in it, not just a prime number, right?
Well, we're not really talking about something. So we're talking about something that's related to cryptography in the sense that it's modular arithmetic.
Okay.
But this is not. I'm not really talking about anything crypto.
So modular arithmetic is basically like a clock.
It's yes, exactly. It is clock arithmetic.
It's where you have a math type where it's.
Yes.
You could say like it goes in cycles, or
it goes in cycles. So and we are doing the dumbest, most simplest case of modular arithmetic, which is mod 2 arithmetic.
Okay.
So when you get to 2, you go back to 1. Simplest arithmetic.
Yeah.
Okay. So very specifically, 0 is the category of even numbers. So it's integers that are 2 times another integer. Does that make sense? That's the definition of 0 mod 2.
Yeah.
So, Mike, if you take any even integer plus another even integer, what is that?
That's still 0.
Or it's always going to be. Well, you're fucking looking ahead. Okay.
No, I'm here. Where you are?
You're looking at multiple. Whatever. If you take an even number plus another even number, it's always going to be even, right?
Yeah.
Okay, if you take an even number and an odd number, so,
5 plus 4, 9.
That's always going to be odd.
Yeah.
Okay, and, there's the algebra. If you take 2 odd numbers, so like 3 plus 3, that's going to be 6, which is an even number.
Okay. Yeah.
And that's kind of the observation
We're
here.
just on a clock with 2 ticks. You just go even, odd, even, odd, even, odd forever.
Oh yeah, that's even
It
better.
was 5 ticks, now it's 2 ticks.
Yeah.
Yes. Yeah.
He made it a lot better.
Yeah. Yes. That's a good diagram, actually. Okay.
And are we talking about this because computers are binary?
Yes.
Okay.
Yes. Okay. So an even number times an even number is still going to... So 2 times 2 is still going to be an even number.
Yeah.
An even number times an odd number, what's that going to be? Think about
it. The other one.
So even because it has 2 in the factors?
Yes. Yeah. So 2 times... So here, I did the algebra here. 2k times... So any odd number is...
If you have 2 in the factor list at all, it's going to be even.
Yes, that's because that's the definition of an even number. Does that make sense? Mm-hmm. Okay. If you take 2 odd numbers and you multiply them together, you get an odd number, because if you do the algebra, 2k plus 1 times 2l plus 1, you FOIL that out, you get 4kl plus 2k plus 2l plus 1, and that's 2 times some integer plus 1. So it's 1 off a multiple of 2, which is the definition of an odd number. Does that make sense?
Yeah.
Okay. So this is the definition of mod 2 arithmetic. These are our 3 operations. And if we look, we get exclusive or, and not. Does that make sense?
No. I don't know what those are. Alex or...
Is the difference between exclusive or and inclusive or?
Right. So exclusive or is an algebraic operation. Right, so you remember earlier when I had the 2 Venn diagrams?
Yeah, the exclusive is the outside of not the intersection.
Yeah, the exclusive or excludes the intersection of these 2. And if you write that as in terms of integers, so we're not in the first set and not in the second set. So here. Actually, let me.
So if this is
exclusive or,
this would be the center of it.
So
that's the center of it.
Here, let me show you. Where the hell is GIMP? So. Oh boy. See, I had a different drawing program that I liked a lot better.
That was pretty good.
And I'm still getting used to this. So this is A, is this circle, and this circle is B. Okay? So LXOR of 0 and 0 means we're not in A and we're not in B. So that's this big region out here.
Oh, so that would be the universe.
Yeah, well, the universe is everything including A and B.
So it'd be the A to the power of C, that universe minus those 2.
Well, actually,
It'd be A and B complement.
or A union B.
So it's everything that's not A or B.
Okay, the universe is everything,
Yes.
including everything
By
in
the
A.
very first one.
Yeah, so that is yes, I see what you mean.
Everything that's not either in A or B.
Yeah, so that's what the first row is like this region out here that is not in either of them. So if we're talking about, A symmetric difference, B,
I don't think he knows what that
I don't know what's in
is. Okay, here's the difference between inclusive or and exclusive or. Inclusive is more inclusive. You
Yes.
say if A is true or if B is true or both, saying like either or both, then you're good, you're true. Exclusive is it has to be only one of A or B. Only A, only B, but if it's both, you're screwed. That's the difference is the treatment of when you have both are true. Inclusive is, it's either or both. Exclusive is one or the other, but not both.
Okay, so the second one is
yeah, you're
B.
in one.
The second one is B. It's the second one.
Yeah, so
The second one is B.
So 0, 0,
Okay, and the third one is A, and the last one is the intersection of two.
correct.
They only
yes.
differ by what do you do when they're both true.
Yes, that's the difference
They
between
behave
exclusive
differently.
and inclusive or.
Okay.
Inclusive or includes the case where both of them are true, and exclusive or includes the case where only one of them is true.
Okay.
You can call it the one or the other operator.
Yes.
Okay. What about this?
And means both of them have to be true. So both of them have to be 1. So if you look at exclusive or and you look at the arguments, here, let me.
And is the intersection operator. It gives you the overlapping part.
Yeah, so exclusive or is true if exactly one of the two arguments is true. Does that make sense?
Okay, so exclusive is true if one of the arguments is true.
One and only one.
One and only one, but not both of
if
them.
both are true.
If both of them are true, which is 1, 1, which is the last row.
Okay.
So 1 means true and 0 means false.
Okay. Yep.
Yeah, so if both arguments are false, then it's 0. Or false goes to false.
Yeah.
False true goes to true.
Okay.
True false goes to true.
XOR is the one or the other.
True goes to false.
Yeah, so they cancel. Okay. And then means both of them have to be true. Both arguments have to be true for and to be true.
Okay.
Okay, and not just inverts the bit. Does that make sense?
Yeah.
Okay. And my point is that if we talk about exclusive or and logical and, these logical operations are the exact same thing as mod 2. So if you look, the two tables are identical. So 0 plus 0 is 0. It's the same as exclusive or. 0 plus 1 is 1. That's the same as exclusive or. 1 plus 0 is 1. That's the same as exclusive or. 1 plus 1. That's odd plus odd is even. Does that make sense? Oh, well, you scrolled way to the end here.
I don't know what happened.
Go back. Go. Jesus Christ.
Okay.
Here, I can escape. And
I'm good.
No. You got to go down a little bit from there. I wonder if there's a way to get tech to generate one that doesn't make a different fucking slide for each.
I could install Adobe PDF Reader.
That might be faster than.
Yeah. Okay. So that's why you decided on mod 2.
Yeah, mod 2.
Because it's similar to it represents.
Because binary, because true false.
Yeah, so the point is that the correct version of what you are about to say was the reason that we're picking exclusive or over inclusive or, the reason that is important is because we now get to use all the tools from math in logic, particularly polynomial arithmetic.
Huh?
Yeah, okay. Bro, what the fuck is wrong with Windows?
No, I'm installing.
Oh, okay.
What's wrong?
No, dude. We were. I was the guy who might be joining later, Craig. He's our. I don't know if he's our lead developer. But we have 3 guys who all could be kind of the lead developer at my job, and he's one of them. And he wrote the HTTP parsing library that I was using, and I was having some weird bug in my web server, my demo is just a website. I was having some weird bug in my web server, and we were trying to figure it out. And he was using his Windows machine just to like see how it worked. Apparently now on Windows, I don't think it ships with like vanilla Windows, but like on their development kit, it like they literally just have like this whole fucking virtualization layer where they have Linux included.
The Windows subsystem for Linux.
Yeah,
It's for consumers too.
Do they just ship that on like vanilla?
It's opt-in.
Okay, but I'm just like, dude, their operating system is so fucked up that they literally ship a whole like fucking virtualization layer with another operating
Apple
system.
unveiled their own copy of
Dude,
that.
I
this
think
summer as
Xfinity gives you bandwidth for speed test, but in reality, it's complete garbage.
It's Google Fiber here.
Oh, it is?
Yeah, you might want to just like tether through your phone or something.
I bet they're like giving it bandwidth for the speed test. Let's try this speed test. This might tell us the truth.
well. It's a very major development in Windows.
Oh yeah, look at this. It was showing like 200 with speedtest.net.
Yeah, that makes well probably because
Scumbags.
I'm probably like live streaming a bunch of shit.
Yeah.
And
okay,
also like this is an old house, and so the walls are Faraday cages, and the Wi-Fi broadcaster is on the other side of the house, so that might be the problem.
Oh, okay.
Nice.
Oh,
Yeah. Oh look, now it's better.
I can look at it if you want.
yeah. Here, I'll go just let the dog out 1 second. There we go. Hey, who's joined?
Hello.
Hey, Jeff. So, Jeff, is Mike's camera working?
Yes.
Jeff is a guy from, it's one of my coworkers.
Nice to meet you, Jeff.
Yeah.
Can we hear him? Let's see.
Yep. Test 1 2.
Hey.
Yeah.
How are you doing? How was fake Thanksgiving?
Not too bad, dude. Thanksgiving
mean
they
fake,
get you.
bro?
They fucking fill you up with food, and then right when you can't eat anymore, they roll out the dessert, so you're nice and comatose for when you leave. It's amazing.
Yeah, it's great. Yeah, so what we're talking about, actually, here we'll record Jeff's thing. Here, we're gonna go back. Can you see my screen?
Yep.
Okay. Going way back. Okay, so this is the the whole premise here is this is a problem in logic, and I'm going to show you a way to solve it that's really like elegant. The problem is there's 3 roads in front of you. There's the one of them's the golden road, one of them's the marble road, one of them's the stone road, and there's a knight in front of each road. And what the knights say, the knight of the golden road says, "This road leads to the Grail. Also, if the stones take you there, so does the marble road." And the knight of the marble road says, "Neither the gold or stone roads lead to the Grail." And the knight of the stone road says, "Follow the gold and you'll reach the Grail. Follow the marble and you'll be lost." All 3 of these knights, each one of them is lying. However, there is a holy grail, and it's down exactly one of the roads. ChatGPT, I got done fighting with AI. ChatGPT finally generated one with the correct number of knights. Instead of just having like weird random ghost knights and like some random road, and then like a bridge and shit like that. But so in the story here, the roads don't converge. But I got kind of sick of dealing with ChatGPT. Anyway, there is a holy grail. It's down exactly one of these roads. The question is which one. You can assume everything that the knights tell you is false. And so I want to record your guess. And if you guess correctly, Mike is going to pay you $50.
Bro, it keeps going up. At first it was split among the winners. Now it's become every person.
No. Well, if you guess it correctly. So Jeff, which road do you think it's down? You're gonna have to. These 2 guys both guessed the stone road. So, what's your guess?
Tell him the guess. You're gonna insert bias into his answer by.
Well, no. I'm trying to make it game theory, because if he guesses the same thing that you guess, maybe he's more likely to be correct.
But you're adding more variables to his guess.
Well, no. But he's an investor. That was how he got started our company, and so like he can. I'm trying to give him a full view of the game.
You're tainting the
knowledge. Okay, yeah. But anyway, so if you guess stone, that's what everyone else thinks. So maybe that's more likely to be correct. But also, if
the crowd can be wrong,
the crowd could be wrong. So there's like an arbitrage opportunity.
And also, we're drunk. Show him the bottle.
Yeah.
So take that into account.
Yeah,
I'm gonna give you all the variables.
Yeah, Mike has drank all of this. I had like one shot, and
bro, I would be in the hospital if I tried.
He's Eastern European, so it's fine. Anyway, so the point is that if he picks marble and marble is correct, then he gets a bigger share of the prize fund because nobody picked that.
True.
If he picks stone, maybe stone is more likely to be correct.
But you get less money.
But you get less money. So there's like a trade-off there. So it's not just purely which one do you think is correct. There's also, if you're not 100% sure, maybe it makes more sense to pick an unpopular option. All right. So Jeff, which option do you want to pick?
I'm gonna go with the Marble Road.
Okay, Jeff's going with marble. All right. And so the basic setup here, Jeff, have you ever tried to learn some formal logic?
Not formal logic, no.
Okay. So formal logic, typically you've seen this Venn diagrams where you have this operation is called the union. So you have two sets A and B. A union B is the set of all points that are in one inclusive or the other. So one, the other, or both. And this is the usual, and then you have this other primitive operation that's called AND, or the intersection in set theory. So the intersection A intersect B is the set of all points that are in both A and B. And then A complement is, all the points in the universe that are not in A. Does that make sense?
Yes.
Okay, so this is the normal setup. And what I'm saying is that actually, if you instead of using inclusive OR, if you instead use exclusive OR as a primitive, and exclusive OR just is the same, except if both A and B are true, then A exclusive OR B is false. Does that make sense?
Yeah.
Okay. And what I'm saying is that if you do it this way, it's actually significantly more elegant. And the analogy I used was that if you use inclusive OR, it's kind of like geocentrism. And if you use exclusive OR, it's kind of like heliocentrism. And it's not that geocentrism is wrong, because it's an equally consistent model of planetary motion. It's just a lot more complicated, and you're making your life a lot harder. And the reason that this is relevant is because if we talk about mod 2 arithmetic, so you're familiar with clock arithmetic. So right now it's 7 p.m. And what time is it going to be in 12 hours from now?
$7 p.m.
Well, it'll be 7 a.m., but it's 7 o'clock now.
Yeah.
12 hours, it'll be 7 o'clock.
Yes.
So that's mod 12 arithmetic, which means when, it's cyclic arithmetic. When you get to 12, you loop back around. Fucking cats. When you get to 12, you loop back around. What we're doing is mod 2 arithmetic, which is the simplest possible version, which is, here. Can you see? Alex made a good diagram of it, which is it's like a clock with two hands, 12 o'clock, or there's 2 hours in the clock. So, yeah, so 12 o'clock is, oh, you know what? I should probably make, here, let me draw.
Even and odd.
Yeah, so it's kind of like, you know, a clock that has two hands. These are evens, which is 0, and then 1, which is odd numbers. Does that make sense? So 0, 1, 2, 3, 4, 5, 6, 7, 8. Does that make sense? So 0 is...
Yeah.
Yeah, okay. So that's the kind of setup for what we're doing. Oh, you gotta push the thing like to the... There you go. You got it. Oh, he's having a smoke break. So that's what we're doing. So the reason that exclusive OR is better is because it maps straightforwardly to mod 2 arithmetic. So exclusive OR is actually the same thing as mod 2 addition. You see that? So 1 plus 1 in mod 2. So if you take two odd numbers like 3 and 3, or 3 plus 5, that's equal to 8. So two odd numbers, 1 is the category of odd numbers, 0 is the category of even numbers. So if you take any odd number and any odd number and you add them together, you're always going to get an even number. Mm-hmm. Does that make sense? So that's what mod 2 arithmetic is. So odd numbers are anything that's 1 off from a multiple of 2. Even numbers are anything that's a multiple of 2. Jesus Christ.
No, you're good.
All right.
I doubt the microphone picks that up.
Yeah, I don't know. It has good. It's always chaos here. So if you look at exclusive OR, you look at these two tables, they're the same table. So modular mod 2 addition is the same thing as exclusive OR. Mod 2 multiplication, so you take any two odd number, an even number times anything will have 2 as a factor. Does that make sense? So here. So if you take 2k times anything, it's always going to have 2 as a factor. So an even number is 2 times another integer, times anything is still going to be even. So if you have any even integer and you multiply it by anything, you're still going to get an even integer. The only way to multiply 2 integers and get an odd integer is if both of the product terms are odd. Does that make sense?
Yep.
Okay. So in the way that this works in mod 2 arithmetic, even integers are those which are 0 mod 2, and odd numbers are those which are 1 mod 2. So 0 times 0 is 0 mod 2, 0 times 1 is 0 mod 2, 1 times 0 is 0 mod 2, 1 times 1 is 1 mod 2. I made a mistake here. Sorry. Yeah. I made a typo, that's all. The slides are in the Discord chat. Mike, why are you looking at gay porn?
I'm not, it's not gay porn. It might look like it, but it's not. I promise.
Okay.
I got distracted, sorry.
Okay, so this is the context of what we're talking about. And adding 1 is the same thing as logical negation. Does that make sense? So that's why exclusive OR is better, is because it maps to mod 2 arithmetic. And in particular, we can take all of our tools from algebra, and it looks like Alex is coming back. I might wait till he comes back to explain this. So, oh, by the way, Jeff, I should have introduced everyone. So Jeff is, here, I'll wait till Alex comes back. Is he coming back?
No, he's smoking.
Well, it looks like he just put a cigarette out. He might be coming back. Or what's he doing?
He might get another one.
Might be smoking another one.
He might fire up another one.
Okay. Anyway, so these are a couple of my friends from Utah. So this guy, his name is Mike.
Hello, I'm his superior in
Mike.
Jiu-Jitsu.
Yes.
I outrank him and destroy him on the mats.
Yeah. You can tell.
But he helps me with some strength training, so it's okay. I take it easy on him sometimes. But yeah. And Alex, he's coming back.
Yeah. So Alex, the red-haired guy, is a friend of mine from high school. Anyway. So so I just got finished with the recap for Jeff.
Alex is not really red-haired. He kind of like dyes it that color, so ice doesn't. Capture him.
He's actually an illegal immigrant.
Almost got
He's on the run. He's on the run. He's laying low right now.
He works for the hell is that cartel called?
So he'll visit anyone that invites him.
No, the one from El Salvador. That
MS-13.
Yeah, he's from MS-13.
He'll visit anyone that invites him as long as not the address on his ID.
Yeah, so he's under deep cover right now. Anyway, Jeff's a guy who works with me. Anyway, so
I told you I don't need booze.
Yeah, I know. Anyway, we can. The reason Mod 2 arithmetic is so important, the fact that there is this direct correspondence, is we can take all of our tools from algebra and just port them over to logic. And in particular, polynomial arithmetic carries over, and there are a couple of rules that make it even simpler. So notice here, if you take anything and you add it to itself, you always get 0. And anything times itself is equal to itself. Also, all of you are chimps, and I don't think any of you have taken a linear algebra course. But linear algebra also carries over in modular arithmetic, but no time.
Well, I know there's a convention that multiplication is an and addition is an or, but which or?
Yeah, so in our case, where addition is exclusive or. Also, there's some carryover to circuits. I'm not actually 100% sure about zero knowledge proofs, but we'll maybe get into that in a later lecture. So observations. X times y is x and y. Also, I forgot to put x plus y is x or y. And then adding 1 is the same thing as logical negation. Anything plus itself is equal to 0. Anything times itself is equal to itself. So 0 times 0 is 0. 0 times 1 is 1. So this is very, very important. Okay. So I should have put this vertically. Let me actually start this over here in GIMP, and let me show you what I mean. Let me make a new. Okay. How do I just zoom in?
Hi, baby girl. You're okay.
Okay.
Baby girl.
So what I'm going to do oh, oops. Okay, so this is what I would call an indicator function, meaning it is equal to 1 on exactly one of its possible inputs, and it's equal to 0 otherwise. Does that make sense? Mike, are you looking over here? Mm-hmm. Yeah, so this function over here, this is equal to 1 if both of the inputs are 0, and otherwise it's 0. And we'll call this first input, we'll call this A, and we'll call this B. And what I'm pointing out is that for each one of these indicator functions, you can cook up a polynomial that equals the indicator function. So in this case, it's 1 plus A. Sorry, that was bad handwriting. this is 1 plus a times 1 plus b. Okay, so remember times is equal to and, so and 1 plus is equal to not. So this is not a and not b. Does that make sense? And then for the next row, if I want, you know, the next one, so there's no way Mike's going to get it, but Alex, can you tell me if I wanted to cook up a polynomial? Here, I'm going to just draw the function just so that I can be clear. So
That's not an indicator function, though.
yeah, because I forgot and I put 1 because I was being dumb. Thank you. So this column is A and this column is B. For this, how can I cook up using a similar sort of idea a polynomial that's going to be equal to this function?
So that's not like if one of them is true, the result is true. That one's different.
Correct. So this function that I just drew here, this is true only if both of the inputs are false.
Okay.
Right?
That's how you read that one. What about the bottom one?
So this one is true only if the first one is true and the second one is false. So if I drew this as a Venn diagram, so we have our whole universe here. This is A, and this over here is B. This is this region right here. So it's only the situation where A is true and B is false. Okay?
Well, it's going to be a product of two sums like the other one, but I'm not exactly sure.
Well, so it's going to be A times 1 plus B.
Oh, sure.
Right? So A and not B. Okay. So this is actually...
No, how is that going to be 1 plus B? Because you're looking at the things that are not in B.
Yes, that's what 1 plus... Because adding 1 is the same thing as negation. Right, here, let's go look at...
Oh, if you're adding 1 to B, it's not B anymore.
Correct. So look, here,
Okay.
see this table? Adding 1 always flips the bit.
Okay.
Does that make sense?
Okay, yeah.
Yeah. So that's the whole concept. So A times 1 plus B. So I'm gonna do the third indicator function here. 0, 0, 1, 1. Okay, for this one, so this is A, this is B. This is the same thing as above, but here I'm just gonna try to draw it as a Venn diagram here. This is A, this is B. And we have our whole universe here. So this is the subset that is in B, but not A. Does that make sense? So it's the same. It's exactly symmetrical to the one above. So by that symmetry.
So would that be B multiplied with 1 plus A?
Correct. Yes.
Okay.
So this is 1 plus A times B. Okay. Then I need another page. What happened? Oh, I'm still not used to GIMP. Okay. Why? Please just. How do I zoom in? Oh, for fuck's sake.
Control scroll.
Yeah. For some reason, no. Stop fucking with me, GIMP, please. So for this one. I forgot you're left-handed. So this is the fourth indicator function. Oh, nope. This is the fourth indicator function. And if we just draw it out, this is A.
Oh, okay. So only the intersection is true.
Correct.
If both of them are true.
Yeah. So
that would be A and B, but it's not like A multiply with B, right? It's not
No,
a
that's
multiplication.
A times B.
it's exactly that, actually.
Oh, it is?
Under
Yeah.
Wildberger.
Yes. Because this...
Under wildberger, A multiply with B gives you the intersection?
Correct, yes.
Oh.
Because...
Because he literally put that on that bulleted list. The first one.
Here, go back a couple slides. Yeah, here, no. That one with the table. Mm-hmm. No, down.
Forward.
There we go. Stop. Don't touch it. So, if we go back here, or this one, this page. We go here.
Oh, anything times itself equals itself.
Correct. Yes.
Because we're in that mod 2 type of thing.
Yeah, we're in mod 2 arithmetic.
So even if it's a prime number, it doesn't matter.
Yeah, it doesn't matter what kind of number
It will be itself. Oh, okay, that's why it's like that.
Yeah.
We're talking about the mod, not normal math.
Correct. Yes.
Okay,
So the
we're in
context,
weird ass math.
yeah, we're in weird ass mod 2 math. Yeah.
Pardon my French.
Yeah.
Wildberger mod 2, right?
Yeah, I mean, Wildberger did not invent mod 2 arithmetic.
But we're in Wildberger mod 2 as opposed to normal bool mod 2.
Yeah, the normal math.
Mod 2 arithmetic works the same way. So Boolean arithmetic does not correspond straightforwardly to mod 2 arithmetic. That's the point, is that, well, Boole's original version does.
Right.
But not the version that you learn if you take a basic programming course. So, if you have 0 and 0, you can cook up a polynomial. So this is not A, which is 1 plus A, and not B, which is, in our language, it's 1 plus A times 1 plus B. Does that make sense?
Yeah.
So each of these functions that's equal to 1 on exactly one of
I
its...
have a question though.
Go ahead.
So we're doing all this to figure out which road is the correct road.
Correct.
But did we choose does this mod 2 apply to the fact to any, what if there was 5 roads or 10 roads? Do you still apply mod 2 or do you have to use a different mod?
No. This will work.
It's still mod 2 because the 2 corresponds to true or false. Does it lead to the grail or does it not lead to the grail?
If you had an in-between option between true and false, then you need a different mod.
Yeah, then you might need... Yeah, if you had more variables that you were trying to represent and there was a direct representation, and there was like an isomorphism, if the structure of the numbers matched the structure of the 3 different...
Mod 2 is because true, false, liar, truth teller.
Yeah. Got
Yeah.
it. Okay.
They work well.
We have a true and false option.
Yeah, it's very specifically though that the structure of the natural structure between true and false maps to the structure of integer arithmetic.
Because when we have only true and false, it's kind of like this diagram.
Yeah.
Okay. Yeah.
Okay.
So for this first one, it's not A and not B. So that's going to match only on 0, 0. So 1 plus A times 1 plus B in weird math. In this one, where we're doing A and not B, that's going to be A times 1 plus B.
Okay.
And this one, where we have, we're doing the third row, is 1 plus A times B, because it's not A and B. And then the last one is only if both of them are true, which is A times B. And if you notice, this is the table for logical AND, or also equivalently multiplication.
Yeah.
Okay?
Okay. Yeah.
Okay, so let's go back. Yes. So, and because it was a slide, I had to put it kind of in this weird janky format here. But all of that information that I just ran through, writing it out, is right here. So 1 plus A times 1 plus B, so this is not A and not B. That gives you the first indicator function. They're oriented differently, so it might...
We have 4 indicator functions.
4 indicator functions because there's 4 possible values, or 4 possible outputs. Or, sorry, 4 possible
Inputs.
Inputs. Thank you. Okay, so an example is what's called logical implication. So the point, the reason that this is interesting is because, you know, all of these god damn it, output functions, these are all disjoint, right? So there's no overlap between these. So if you want to get an arbitrary, you know, 1, 1, 0, 1, you can just XOR these to get, you can just XOR the ones that are 1 together to get that. Mm-hmm. Yes. And then you can just reduce it. So, right, any arbitrary function and or / truth table, it can be converted to a polynomial by just taking the indicator functions that are 1 and XORing them together. Does that make sense? So in this situation, because it's, you know, 3 1s and only 1 0, it's easier to compute the opposite and then just add 1 again. Does that make sense? So we're going to do the opposite of A implies B. So not A does not imply B, which is and kind of, it's kind of a little janky to realize that this is the truth table for if A then B. But if you draw out the Venn diagram, it makes a little bit more sense. So what is the set of all points such that if X is in A, then X is in B? And it's this set. So it's basically, you know, it's the opposite of this. So the white region is what we're doing here, which is A times 1 plus B, which is the third indicator function that we just did. And that's the white region here. And so the blue region is 1 plus that. So this is, and then so if we compute that, we get 1 plus AB. And something that's very, very, very important, which I didn't really prove in these slides because I didn't particularly think about it. Oh, let's check actually by going the other way. So we're going to compute for each possible pair of A and B, 1 plus A times B. So for 0 and 0, that's 1, which is A, plus, or 1 plus 0 plus 0 times 0. 1 plus AB. Does that make sense?
No. I've lost you. I have no idea what you're doing here.
So we remember where. So you were following when I computed.
Yeah. What is this like line like that? A line to B like what
So that is standard mathematical notation for if A then B.
A implies B.
A implies B, like what does that mean? Like the A is B or what?
Anytime that A is true, then B is always true. But there could also be cases where A is not true and B is still true. But it's saying that if A is true, then B is true. That's the arrow. That's
what that arrow means. If A is true, then B is true. So I drew out that diagram so that you can see, like, so the only time that, so the set of all X such that if X is an element of A, then X is an element of B. The only time that that is false is if A is true and B is not true, because then it's not true that if X is in A, then X is in B. It's a little confusing.
Yeah.
I think you should probably use the inverse of that diagram.
Yeah. So
it doesn't match the caption.
Yeah. So the blue region is the set where A implies B, but if you take the opposite, that's the white region in that diagram. Mm-hmm. Which we already, I explained, you know, here. That was one of the indicator functions that we already computed.
Okay.
Right. That's where A is true and B is false. And A implies B is, you know, the complementary set of that, which, so the white region is this thing and the blue region is everything else. So.
Okay.
Yeah. So what we're going to do is we're going to compute the polynomial that corresponds to the white region. Does that make sense?
Yeah.
And then if we add 1 to that, that is equivalent to negation, and that'll give us the blue region.
Okay.
Does that make sense?
Because we're in that weird ass mode 2.
Yeah, we're in the weird ass mod 2.
Okay.
Okay.
Gotcha.
So A times 1 plus B, because it's A and not B. So all elements that are in A but not in B. Mm-hmm. That, if we multiply that out, it's A plus A times B.
Elements that are in A but not in B are these, right?
Yeah, that are in the white region.
A plus AB is the white.
Yeah.
Yeah. And then so to get the blue region, we add 1. Mm-hmm. So 1 plus A implies B. So 1 plus A implies B is A times 1 plus B. Therefore, A implies B. We add 1 to both sides of this equation, and we get 1 plus AB.
And that's the blue.
That's the blue region.
And this notification, what is this sign here? A to B, like this?
The double arrow means A implies B. That means if A, then B.
So A implies B means it's everything that's not A?
A implies B. Okay, the definition of A implies B is the blue region.
Yeah, so that's not A.
Yes, so it's everywhere that if A is true, then B is true. The only subset of that graph where that's not true is A, is the white region.
Okay.
Does that make sense?
Yeah.
Okay. Yeah, sorry. Yeah. Yeah. Okay. Now what I'm going to do is, so we computed the polynomial that corresponds to the blue region. And just to double check that we're not, in crazy town, we're going to go the opposite way. So we're going to start with the polynomial and make sure that we computed the correct region. So notice here that, so A and B, so if A is 0 and B is 0, then what is 1 plus 0 times 0?
It's 1.
Right, okay. If A is 0 and B is 1, so let's actually go back to the previous one. If A is 0 and B is 0, Mike, that corresponds to this outer region of the
universe.
The universe that is, right. Mm-hmm. Okay, the outer part of the universe.
Because I'm not in either of those.
Yes, that's correct.
Yeah.
If A is 0, so we're not in A, but we are in B, that's like the opposite half moon.
It's just the B slice.
The opposite half moon there. Yeah. Okay.
The other one is the A white slice.
Yeah, so, and then 1, 1.
The bottom is intersection.
Is intersection. So, the way that the coloring works is 1, if we have a 1 on the region, then it's blue, and if we have a 0 on the region, then it's white.
Okay, that's why you only chose 2 colors.
Yes.
Okay.
Yes. Yeah, that's why I chose 2 colors. In hindsight, it would have been better to pick multiple colors, but...
But no, it does make sense.
Yeah.
It makes sense.
Okay, so... And what I'm saying is I'm claiming that this polynomial agrees with this function, or with this truth table. And what I'm doing is I'm starting with the polynomial, and I'm evaluating it on all 4 possible pairs of inputs, and making sure that I get back the same thing. So I'm just going the other way. So A plus B, if A is 0 and B is 1, then we have 1 plus 0 times 1. Nope, I screwed up. This is 1 plus 0 plus 0 times... Yeah, I just fucked up, sorry. Yeah, there's a typo here. So this is 1 plus 0 times 1, which is 1.
Yeah.
Okay. 0 is 1 plus 1 times 0. So A is 1, B is 0, 1 plus A times B. So that turns into 1 plus 1, which in our mod 2 world is 0.
Yep.
Is that making sense?
Yeah.
Okay, so if both of them are 1, then we have 1 plus 1 times 1, which is equal to 3, which in mod 2 is 1.
Yeah.
Okay?
Yeah.
There we go. All right. I have actually given you enough already to solve this lying knights problem. So our methodology, we're going to use my demo, and I'm going to explain the demo. And what we're going to do is we're going to represent each of these things that the knights say in terms of connectives. So the gold says is gold and stone implies marble. Does that make sense?
Yeah.
Right. Marble says not gold and not stone. So what the gold guy said was, this road leads to the Grail, and if the stones take you there, so does the marble road.
Got it.
Mike, are you following?
Yes.
This is what you wrote here.
Yeah. That's what I didn't write it in a, yeah.
Okay, and what the marble says is, neither the gold nor stone road lead to the Grail.
Yep.
So not gold and not stone. And the Knight of the Stone Road says gold and not marble. So he says, follow the gold and you'll reach the Grail, follow the marble and you'll be lost. So all three knights are liars. We're gonna take each of these things and represent them as polynomials. And all three knights are liars. So we're gonna compute not gold says and not marble says and not stone says. And we're gonna compute the, that whole thing. And then exactly one road leads to the Grail. That means exactly one of the following here will evaluate to 1. Does that make sense?
So with the not gold says, you basically created variables, right?
Correct, yes.
Okay. Yep.
Yeah, so my demo. Can open it up if you want. So what it is and how it works. So it's a Lisp interpreter for a domain-specific language that I designed. The initial concept is to reduce these expressions to these canonical polynomials. So one very important thing that I didn't prove here is that if you have two things that are equivalent as functions, when you reduce the polynomial, so you represent it as, it's not like 1 plus a times 1 plus b, you multiply everything out and it's just a flat sum of these. So here, let me just write it all out. So the basic data structure is called a sentence. So if we consider 1 plus a times b, there's kind of 3 levels here. The letters are these variables, a and b. The words are products of letters. And then 1 is represented as the empty product. And then sentences are sums of words, and 0 is the empty sentence. And then the sentence 1 is the sentence containing only the empty word. Does that make sense? Okay.
To me.
Yeah, Jeff, are you following this?
Yeah.
Okay, Mike, are you following?
Yeah. I am following.
It's forward Polish notation, so the plus goes before everything.
You said Polish notation?
Polish notation. Have you ever done reverse Polish notation?
No.
Okay. So
I know it's Polish sausages and
okay.
Polish people like to drink.
Okay. So
Notations.
no, that's what it's called, is reverse. So on old-timey calculators, instead of putting in 0 plus 1, you would write 0, 1 plus, and then it would compute.
Oh, I see. Okay.
Yeah. So here it's
this on the left is Polish notation.
Yeah. If you do it with the operator in the beginning, that's
So
called
why would you do it that way, though? What's the advantage of that?
I'm about to explain that.
Okay.
But anyway, so in terms of the data structure, if we take 1 plus a times b, the way that this is represented is plus means this is a sentence, times means this is a word. So this
How
is
do you
this.
know about Polish notations?
Programming.
Yeah, programming. It's just if you take the sum of the empty word, so the empty word, 1 is the multiplicative, it's a phrase, multiplicative identity. Does that make sense? So 1 is the empty product. And then a is the product containing only a. And then a times b is the product containing a and b. And then the sum of all of these is the sum of these 3 words. Is that?
What's this bigger than?
Oh, that's just indicating that was something
It's
you
like the
typed in.
terminal prompt when you type
A different line?
Yeah, it just means that you typed this
It
in.
means go ahead and type now.
Okay.
Yeah.
Type that and then the next line.
Yeah, that's all that the greater than means. It's not part of.
So this would be A plus 1 times AB.
Yeah,
right?
1 plus A plus AB. So like here I have in the bullet point, consider 1 plus A plus AB.
Gotcha. Okay.
Okay. So 0 is the empty empty sentence, and 1 is the sentence containing only the empty word. Does that make sense?
Yeah.
Are you following along? Okay. Cool. So the reason that you use this, the reason that you would ever write your notation like this, it's a language called Lisp, or it's a family of languages. The basic concept is that when you have a compiler, and the compiler is trying to represent your code, so the compiler is what translates your source code that you write in a human readable language like C into something that the computer can understand. So it translates it from human readable source code into machine code.
Yeah.
And every compiler that I've ever encountered, it starts by representing code as a syntax tree. And the concept of Lisp is the compiler needs to represent your code as a syntax tree, so why don't we just have our notation be syntax trees? And then it gets really crazy from there, because the syntax of the language is a first-class data structure within the language, so then you can write transformers on the syntax of your language, and then you can, it gets really fucking wacky really quickly. Because you can start modifying the syntax of your language within the language.
Go Racket.
Yeah. So there's hundreds of Lisp languages out there. There's Emacs Lisp, there's Common Lisp, there's Scheme, there's Racket, there's LFE, which is Lisp flavored Erlang, there's Clojure. All of them are interesting. None of them are useful. They're a great choice for learning how languages and compilers work. Which is why you'll see nerds who have, don't actually write software that works, talking about how great Lisp is. It's a terrible choice for actual software. There's only 2 pieces of actual software out there that I know that are written in Lisp. One of them is Emacs, and the other one is Reddit, which I think they rewrote in Python. I do have a special place in my heart for Clojure. I love Clojure. I do love Lisp. I have, it's a really beautiful idea, but it's one of those things. It's kind of like postmodernism, where it is actually a really cool idea. It's sort of correct, but if you put that idea in the hands of average people, they only do terrible things, and so that's why Lisp isn't really very useful. So, syntax of my language. The default behavior is to coerce the input to a sentence. So, if we look back here, it basically took whatever input you had and coerced it into a sentence. So, a sentence is a sum of words. A word is a product of letters. Okay? So it takes whatever input you give it by default and coerces it to a sentence. So this is the definition in my actual parser of all the possible syntax of the language. This is literally my parser. So letters are the same syntax as Erlang atoms. I don't know if either of you have ever played with Erlang. So it's, Alex, you can read regular expressions, right?
Sure.
Yeah, so what this means is that it has to start with a lowercase letter, and then it can have the star means arbitrary amount, so 0 or more of not positive letters, capital letters, lowercase letters, numbers, and the underscore. So we just go to 2, and I just that's totally fine, is to do that. But if I do apple like that, it'll say, hey, so capital letters are patterns, which are variables in the language.
You're like the, what is it, linkages or whatever, connectives.
I'll talk about those in a second. But basically, these are just symbols. So if it starts with lowercase, then it's a symbol. If it starts with uppercase, it's a variable. If I instead do define apple to, plus AB, so that just says no op, and then I type apple, then it. So Mike, are you kind of following along?
No.
Okay. No, all I'm saying is that if something starts with lowercase, then it's a math variable.
Okay.
And if it starts with uppercase, then it's a language variable. It's like a programming variable. That's all. Okay?
But do we care about that? I mean, why do we care about that?
I'm just showing you how to use my demo. That's why I'm explaining this.
Oh, okay.
So
I won't be using it.
Okay. So patterns are the same syntax as Erlang variables because I wrote this in Erlang. Snowflakes, that's what I just called built-in.
So your demo can answer that question, basically.
Yes. So we're gonna use my demo to answer that question. You can do it by hand, but it's really tedious.
Yeah.
It's a good exercise, but it's very tedious.
Okay.
So the snowflakes are the built-in functions. So this is the syntax. So it's defined. These are all of the built-in functions.
Is IFF.
So
if and only
basically,
if.
you're telling us like your technical papers for the demo now.
Yeah. This is just how to use the demo. That's all.
Oh, okay.
That's what this is.
All right.
So, and I'm going to change all of this because, and I'm not going to document anything. The documentation is the source code.
Yeah.
So if you want to learn how to use it, go read the source code. I'm a firm believer in that. So tilde define the pattern. So define pattern to something. The second argument must evaluate to a sentence. Is simple, and then you can undefine. And exclusive or and inclusive or, these can take arbitrary number of arguments.
Variadic, I was wondering that.
Yeah, and then not implies implied by an IFF. IFF just means both implies and implied by. So implied by AB is implies AB or implies BA. Does that make sense? Mm-hmm. And IFF is if and only if, so it means both of them are true.
Right arrow, left arrow, double arrow.
Yes, exactly. So here's how we're gonna run it to get this. So we're gonna define a language variable called gold says, which is this road leads to the Grail, and if the stones take you there, then so does the marble road. Is that making sense, Mike?
Yeah, and his statement is false.
Right.
Yeah.
And then we're going to define what the marble guy says. Neither the gold nor stone roads take you to the Grail, so not gold and not stone. Mm-hmm. And what the stone guy says is this road leads, or what was it? Follow the gold and you'll reach the Grail. Follow the marble and you'll be lost. So gold and not marble. And then all three of them are liars is not what the gold says, not what marble says, not what stone says. We're going to take the and of all three of
the
those.
The reverse of and of all of those.
Correct. Or the
okay,
and,
so you're taking the intersection of all their lies, basically.
Correct.
All liars are saying, and these are all lies.
But you're flipping their lies.
Correct.
That's what I kind of did in my head.
Okay.
You're not flipping their lies. You're flipping their claims.
Yeah.
You're
thereby
flipping
getting lies.
Correct. Yeah. You're flipping. Yeah. You're saying, okay, all three of these statements are false, and we're going to say if all three statements are false, then is it down the gold road?
And it's going to tell you whether that's true or not.
Yeah. If all three statements are false, is it down the marble road? Mm-hmm. And if all three statements are false, is it down the stone road? Mm-hmm. Okay, moment of truth. All right, so I'm going to copy this over
your
here.
PDF ends.
Yeah. This is...
All right.
Okay, we're gonna run... I wrote these out so that we could...
So you're going to run that in there?
Yep. And I made sure that this demo specifically worked. And by the way, this language is only like complicated enough that it specifically can run this demo. And
You try to read the source code. Is it a SAS solver?
Kind of. Wildberger has a video about that specific problem, and his whole thing is that like that's the wrong question to be asking,
Okay.
and he's like, okay, this answers a different question. So, okay, so if we run that. And we ask, what the gold guy said is turned out that was, if you write that out as a polynomial, it corresponds to this polynomial.
Okay.
So it's G plus GMS plus GS.
Okay.
Yeah.
Which is like the truth version, because we already put on a not to say he's a liar.
Well, this is just what he said.
Oh, okay, that's just what he said.
Okay, yeah. Okay, and then we can do... Okay.
One more parenthesis.
Yeah. Okay. So this one should be pretty easy to compute. It's 1 plus gold times 1 plus stone, right?
I don't think Jeff can see that.
Jeff, I'm screen sharing, aren't I?
Oh, okay. He can see.
Okay.
Oh, I see. Okay.
Yeah, not gold and not stone. So if you go back to here, this is one of the first ones we did. Not gold and not stone. If we compute that out, that should be, what? 1 plus A plus B plus AB. So, and if we do not gold and not stone, it should look kind of like that.
Right, 4L.
Yeah.
Yeah, the stream doesn't work.
Yeah.
It's so weird.
Yeah, so 1.
But it works for him.
It probably isn't working because you're on my same Wi-Fi.
Yeah.
It's probably some stupid bullshit like that.
Yeah.
But anyway, 1 plus gold plus stone plus gold times stone. Is that making sense?
Yeah.
So
Based on what Marble said.
Marble said, yeah.
So you define what those guys said, and with the
as polynomials.
Okay.
Okay. Yes.
According to the rules that you set up in your programming.
Yeah. And then stone says, and gold and not marble. Not and define.
So okay, let me ask you something. What if you don't mention non-marble? You omit what the stone says. One of the stone things. Can they still answer it?
That's actually a good question, and let's answer the question, and then we'll circle back to that. Okay. So, and then stone says, so that is 1, so gold times 1 plus marble, so that would be G plus G times M. Yep, here we go. Gold plus gold times marble.
Okay.
Okay. Then we're going to define all liars as and not gold says, not marble says, not stone says.
3 parens.
Not and define. There we go. Okay. Okay. And it turns out that is S plus G times S is what that will evaluate to. If you multiply all those,
So that tells you the truth.
Right. So
gold and stone.
So stone. So here, actually, let's draw that out as a Venn diagram.
Gold and stone exclusive or just stone.
Yes. Yeah. So here, this is kind of heady if we want to like actually think about what this means. So in this case, what it is it's a Venn diagram with 3 circles. So
it's either both or just stone, but not both.
Yeah. So there's 3. So this is gold, marble, and stone. And then what was the expression?
Golden stone.
Golden stone XOR just stone.
Okay. Gold and stone. So it's this region right here, this little moon, XOR stone. So that is going to be...
Is it?
This?
No, because you're going in marble.
Well, I guess you
Let me think. Wait, no. Gold and stone.
XOR stone.
Yeah. So it's actually the stone.
Okay, let's just do this once. God damn it. No, fucking hell.
Control Y.
Okay, you know what? Fuck this. I'm just going to do
Control
it.
Y.
Again. And let me just pick a different color. Okay, so gold XOR stone is this part.
Gold and stone.
Gold and
Those are
stone
primitive.
is that. And then stone, let me pick another color.
Yeah. XOR with the proposition stone.
And then stone is this region.
Right, so if you're either purple or green but not both,
Then it's just yeah.
Then it's
It's what's left of stone.
yeah, and it'll be that's
either green or purple but not both.
Use yellow because
yeah, okay.
it's like gold and it gets more confusing.
Yeah. So we're talking about this.
But no, it wouldn't go all the way up there into marble. You would stop.
Why? Why?
Because marble is out of the question.
No,
No,
it
because-
never said not marble.
Yeah, we never said that we are excluding marble. So if we look
Oh,
at
we didn't say? Well, no, it said gold, stone, and stone. Yeah,
Gold
where's
and
marble?
stone,
There's no
XOR
marble.
just stone. But that means you do go.
it means that marble doesn't factor in. We're just ignoring marble.
Exactly.
Oh, okay.
Yeah, it means that it's like I don't even think about you.
Okay.
It's like, imagine some chick saying that. Okay.
Okay.
Okay. So
I can't because chicks never say that to me, but it's cool.
okay.
Maybe Alex might say that
Okay.
to Alex.
Okay. Anyway.
Giving you crap.
So we're gonna ask, does this imply gold?
Well, it's similar to the other one, but it has an extra.
Yeah, so it gives the same thing, but basically it's like maybe, but it says
Right.
it's conditional on this.
It's like a partially bound function still.
Yeah. So it basically is saying, what is the subset of this such that, what is it? Yeah, it's confused. I have to think about it for a little while.
Was it saying anything different than what you got here? Just because
Well,
there's that extra one?
It's literally just the opposite of this, because it's adding one. So it's the complementary region.
Okay. Does all liars imply gold? It's a partially bound function.
This is saying is basically that is true if you were in the complement of the gold region here.
Okay.
So if we, were to zoom out to the whole,
If not gold, then that.
let me swipe.
My problem with this all night has been that I forget we're in mod 2.
Yeah, it takes.
So
a
it's
minute.
like my brain goes to the
Yeah.
normal mathematical
Yeah.
universe.
Here's your 4
Yeah.
rules.
Yeah. So another way to think about it is what we are asking is this gold region a subset of gold? And it is saying that is true in okay. So what the answer to the question we are asking is, what is the region of this entire graph here where the gold colored region is a subset of G? Okay. And the answer that it gave us is everything that is not the gold region.
Right.
Okay. So if we ask, what is the subset of this graph such that the gold region is a subset of marble, it's basically going to pull out. How is that going to work?
We'll try it.
Yeah, it's gonna exclude this stone part, right? It's gonna exclude just the part of stone that's only in stone and not in the other two. Does that make sense? Mike, are you following along?
Yes.
Okay. Jeff, are you following?
Yeah.
Okay. Okay. Yes. So implies.
Cool microphone.
Yeah. If you want a microphone that like really punches above its weight in terms of audio quality relative to price, this is the answer.
That's awesome.
All right. Yeah, so that's giving you a really complicated thing, but if we think about it, this is, so 1 is the entire space, which is everything, and then we're XORing that against gold, marble, stone, which is the middle.
Mm-hmm.
XOR the, I'm curious now, if we do, oh wait, duh, it's just going to remove the 1. But anyway, so I bet if we drew that out as a Venn diagram, so we ask, so what is the region of this graph such that the gold region is a subset of M? Yeah, so it would need to cut out this specific part, which is like the little part that's just in S and not in the others. Does that make sense? Mm-hmm. So the answer is stone, because if we ask, okay, what is the region of this graph such that the gold part is a subset of S?
The gold color is a subset of S.
Yes, that such that the gold color is a subset of S.
Just that little.
Yeah.
That little one.
Is that making sense? Mm-hmm. It's the whole graph. That is true everywhere in the graph. Mm-hmm. So if we do implies all liars stone.
It gives you 1, and then that means it's true.
That means that's true.
Okay.
So it turned out that the answer was stone.
Okay.
Both of you were right. Mike, you owe Alex $25.
And the other
great.
25 goes to Mike.
Yeah, so good job.
But putting there implies Mike does not have $50. What does your software say?
I mean, you don't have $50, but you. Well, I mean, I'm gonna have to hire some people to come after you. Some of your compatriots. Okay, so that's the end of my presentation. There's a couple of things. One thing that I wanted to. That's a very, very, very important point that I wanted to hit that I guess forgot to include was that every function, every truth table has a unique representation in terms of a polynomial. Well, after you reduce it.
You get to minimally reduce, because you could have a case where you programmed it and then you do this and it doesn't minimally reduce and it's confusing. Like it gives you something that, yes, is equivalent to 1, but it doesn't reduce all the way to 1.
Can you define what the stone guys say without him saying one thing? Can you redefine those variables and then see what it spits out?
That was his earlier question about what if you exclude one of the knights? How to
Oh, yeah. So let's actually just do...
Can you redefine it, or do you have to start from scratch?
If you change the variable... So it does strict evaluation, to answer your question, meaning so like...
So you define the stone guy again?
Yeah, so if I change what stone says, it's not going to propagate to changing what all liars says.
So you have to retype everything.
Yeah, you'd have to go retype everything. But
Okay.
let's.
Yeah, let's start from
you
scratch.
had an interesting question, which is let's do GS liars, which is so if we gold says and not stone says, and then 3 parens, right, Alex?
I think so.
Yeah. So that's 1 plus gold. So if we exclude the information from
Because
the
1 is
marble,
the universe.
Yes.
1 XOR gold. Universe XOR gold.
That's gold complement. G complement.
That's the complement of gold, yeah.
Yeah.
So
Yeah.
it changes the answer.
So if you had only those 2 knights and the other one was just mute
Yeah.
for some reason, it's telling you, okay, definitely not gold. So it's getting you part of the way, but not all the way to the answer.
Oh, okay.
Yeah.
So it eliminates a possibility.
Yeah. So that's interesting. So if we say define, I'm very curious, MS liars, and not marble says, not stone says.
3.
There we go.
So now you're only taking account only what the gold guy says.
Or
Right?
we're ignoring what the gold guy says and
Okay.
ignoring. So in that case,
Well, let me give you the answer on that. So neither the gold nor the stone leads there.
so it's the XOR of all 3 intersections.
Yeah, so the gold does not follow the gold and you reach your folder now, you'll be lost. It would be
all 3
marble
acorn shapes.
It'll be marble.
Yeah, it'd be all 3 little of the weird orange slice shapes XORed against each other.
It'll be the marble. If you eliminate the first one, it'll be the marble. Do it.
Well,
MS,
It'll say
GS.
marble.
He's saying to do GM liars.
oh, okay.
Because you're eliminating what the first guy says, the gold guy says, right?
Yeah.
Okay. It will say the answer will be marble.
Not what gold, not marble.
Oh, hold on.
No, you let the marble.
Gold
knight
says
speak.
and marble says.
Oh,
Marble
Jesus
speaks.
Christ! Thank you.
Yeah.
Marble says.
You're taking out what the marble says?
3.
We're ignoring what the stone guy says.
No, ignore what the gold guy says.
We already did that.
we
That's
already-
MS liars.
Oh, what did it say? Did it say marble?
No, it gave. So it said it is the exclusive OR of gold and marble, the intersection of gold and
It's a
marble.
non-answer. It's kind of like unable to
okay.
answer.
Yeah,
It
it's
doesn't
saying
know.
okay. It's saying
It got
basically
confused.
if you ignore what the gold guy says.
Okay.
You need all 3 to really get an answer. I don't think any of the
Yeah.
2-night combos is going to actually answer.
Yeah.
Too many possibilities.
Yeah. So gold, marble, stone, which is the small region in the
Center
intersection,
one.
XOR stone.
So that still gives you stone.
In the middle.
It says what this is saying is it's saying this is the region of S that is not the intersection of all 3. So it's like the
Okay.
region of the Venn diagram that isn't where all 3 of them meet.
Oh, okay. Yeah.
Yeah.
So it throws it off. You need all three.
Yeah, you do need all 3. That was a really interesting question, though.
Yeah.
Okay, that's the end of what I have to say. Does anyone have any questions?
I did.
Can we use this to break some AI, like jailbreak some AI with this? Like we give it a prompt with these knights, and then Grok goes to shit.
I mean, I don't think so. Anyway.
You have the nomenclature WF algebra.
Oh,
W is wildberger.
yes. F was because it reminded me of the language brain fuck, but I didn't
Like
want to.
BF, okay.
Yeah, yeah.
And what is WFC?
The WF compiler. Yeah.
Okay, next time we do a stream, it needs to be more entertaining, not about this math bullshit.
Not about this math bullshit.
Yeah, it's gotta
That
be
is all my questions.
more fun.
Okay. And
Something that I can participate in.
okay, so where to find the Wildberger video? There's a link at the end on the last slide.
To the SAT solver video?
Or to his playlist about this,
That's
and one of which is the SAT
Oh, and it's on Rumble. Good for him.
Or no, those are videos where I was explaining this to Craig.
We need
who
to
was-
do like a jujitsu stream or something else.
Yeah.
More fun.
and then
like
these are
boring stuff.
Wildberger. This is prior lectures that I've done that were on Rumble
All right.
because that was when YouTube was at its peak of its censorship. All right, thank you all for coming. Jeff, do you have any questions?
Oh, that was a fun presentation.
Yeah, thanks for jumping in, Jeff.
Yeah. All right. I guess that's all.
Yeah.
Thank you guys for coming.
To your other friend, Ohio gozaimasu.
Yeah.
The what?
To Craig.
Oh.
Yeah. I'll tell him you said
You
that.
say some Japanese stuff?
Anime o janai shimasu.
Yeah.
Holy cow, dude, you're like an encyclopedia.
Is that Craig? Was Craig in here? Or am I...
No. I think he
No.
probably is lazy getting up, or he's like actually doing his job instead of fucking around with us. All right. See you guys. Hi there. So, I was about to make a point at the end of the video, and Mike distracted me, and so I want to make that point right now. And that point is that any two polynomials, or any of two of these sentences that look different, evaluate to different sentences, and I want to explain why that's true. This isn't a formal proof by any metric, but if it contains enough detail that you can massage it into a formal proof. I don't find proofs particularly enlightening. I find so. So just remember, letter is one of these things. A word is a product of letters. A sentence is a sum of words. Okay, so I'll say a polynomial is reduced if and only if it is a sentence. So colloquially, you expand out all the terms. It'll expand into something that's a product of a bunch of words. So what I want to prove for the math people in the audience, there's a bijection between functions and sentences. For everyone else, every function has a representation as a sentence. We already explained that. You just use the procedure where you XOR the indicator sentences together. The representation is unique. So if two sentences are equal as functions, then they are equal as sentences. So that's the less obvious thing that I want to prove. Equivalently, if you have two sentences that yeah, the equivalent of this is the contrapositive. So if they are second. The equivalent of this is the contrapositive. So generally speaking, if you have if A, then B, that's equivalent to, you can check this with WFC, if not B, then not A. So if two sentences differ as sentences, then they differ as functions. So these two statements are equivalent. So essentially what we want to avoid is the following situation, which is where we have two different sentences, and then you go to evaluate them on all the inputs, and you get the same function. And I want to just prove that that's impossible. What the hell? Okay, so argument outline. First, I'm going to give you a counting argument that's just going to kind of illustrate why this is plausible. Then I'm going to give something resembling a proof. So the counting argument is just to prove that there's the same number of sentences as there are functions given, an arity. So there's the same number of sentences with two letters, possible sentences with two letters, as there are possible functions with two arguments. So suppose we're talking about arity 2 functions. So we can call the variables A and B. Then there are 4 possible inputs, because there's two inputs, two choices for each input, 4 possible inputs. Then for each input, there's 2 choices for the output. So therefore there is 16, which is 2 to the number of inputs, possible functions. And this generalizes. You can check for arity 0 if you want, but there are 2 to the arity possible mod 2 functions for any given arity. Okay, likewise, there are 4 possible words. A, B, and AB, or 1. You can think of these as having bit flags. So empty empty is 0 0, empty A empty is 1 0, and so on. Oh, this should be 1 1. And you can see it's the same argument essentially. There's 2 to the not arity number of letters, possible words, 2 choices to include or exclude for each word, hence 2 to the I shouldn't have said arity, I should have said number of letters, number of distinct letters, possible sentences. Okay, so this should convince you at least that what I said is plausible. There's the same number of sentences as there are functions, and this holds for an arbitrary arity. Again, for yourself, make sure that you check that this is true for arity 0. If there were more sentences than there were functions, we'd be in trouble. So multiple sentences would have to evaluate down to the same function because that's how counting works. Likewise, if there were more functions than sentences, I have no idea what would be going on. You would have functions that couldn't be represented as sentences or something. Maybe sentences would have ambiguous evaluation because I don't know what would be going on there. But thankfully, we're in we live in the universe where same number of sentences and functions. All right. Since we know that the two collections, so functions and sentences that have the same arity, are equal in number, all we have to prove is that one collection enumerates the other. So there isn't some weird situation where, let's say the x's are the sentences and you have two different sentences that evaluate down to the same function, and there's some function that's an orphan. So I don't know. Actually, the counting argument might have proven it already. Well, I think what's not clear, because it's possible to construct a sentence for every function. What's not clear is that when you go to evaluate that sentence, you get the function back. So actually, I think that we do need this counting argument, or this argument here. But whatever, I'm just trying to convince you that this is true. I'm not going to be super rigorous because I don't like being super rigorous, because I find that you can take rigor way too far and you end up sacrificing clarity for rigor, and I almost always will choose to avoid that trade-off. I think the proper setting for rigor is when you're like writing a computer program and you actually do need to think about all the corner cases, and then what rigor means in that context is much different than what it would mean in math. So anyway, let's assume that we have two different looking sentences. So we have sentences that have different terms, but for somehow, some way, they're equal as functions. So I'm going to prove a statement that's impossible given that premise, and that therefore falsifies the premise. So different looking means one sentence, we have sentence 1 and sentence 2, and one of them has a word that isn't found in the other. And what I'm going to do is I'm going to XOR them together. So, for instance, let's say sentence 1 is 1 plus A plus AB. Sentence 2 is 1 plus B. And then sentence 3 is going to be, well, we just XOR. We get A plus B plus AB. Okay. So since sentence 1 and sentence 2 are equal as functions, then the sum here must evaluate to 0, because evaluate this function, XOR evaluate this function, the results must be the 0 function, because we already established all that. So since S1 and S2 are different as sentences, the sum S3 must be a non-empty sentence. Otherwise, yeah. Meaning it's not all zeros. So the question is, is it possible for a non-empty sentence to evaluate to the 0 function? And if that's possible, we're screwed. But if not, it might be the case that different sentences, it must be the case that different sentences must evaluate to different functions. Okay? So the goal now, so we've refined our goal. We've said, okay, if we have two different sentences, their sum must, and they're equal as functions, we add the two functions together. They must cancel out and equal the 0 function, because anything plus itself equals 0. But the resulting sentence would be a non-empty sentence. And so if we can prove that all non-empty sentences do not evaluate to the 0 function, then we're done, because we falsified the initial premise. So again, we're going to always go back to definitions. That's generally speaking the best way to prove things, is just write out definitions. And that's almost always the simplest way to prove things, is just what are the definitions? You don't need to be fancy. So consider S3 as a set of words. So the words are themselves sets of letters. So a sentence is just a set of words. Word is a set of letters. So the words can be partially ordered by inclusion. So meaning if this word is a subset of this word, then we'll say I wrote less than or equal to, but this word A is a subset of the word AB, and B is a subset of the word AB. 1 is, of course, a subset of every word because it's the empty word. And A and B are, of course, not comparable. So this is what it means to be partially ordered by inclusion. It's not totally ordered. An example of a totally ordered set would be like the integers. The integers are a totally ordered set. Given any two integers, they're either equal or one of them is bigger than the other. That's not necessarily true here. This set is, strictly speaking, bigger than this set. This set is smaller than this set. This set smaller than everything. These two are not comparable. The set of words in S3, the set of words in S3 is a finite, non-empty, partially ordered set. So that's a partially ordered set. So the set of words is itself partially ordered. So that means that must contain some lower bound, not necessarily universal. So what I mean by this is, let's consider A plus B plus AB. So both A and B are lower bounds, meaning that there isn't another word in the sentence that is smaller than this one. 1 plus A plus AB. So neither A or B are lower bounds because star is there, 1 is there, and 1 is the universal lower bound. You get the point, is that we can kind of pick some word that's in the sentence that is not a superset of another word that's in the sentence. The purpose of this entire exercise is that I want to cook up an input for the third sentence where exactly one of the words in the sentence evaluates to 1. So one of the summands will evaluate to 1, and the rest of the summands will evaluate to 0. If you have a word that is a superset of another word, you might run into a problem. So let's say we have B plus AB. And let's say that we chose randomly. So we chose AB as our word, and we want that to evaluate to 1. So we're going to cook up the input. A is equal to 1 and B is equal to 1. So let's go evaluate. Well, we have B plus AB. Oh shit, that's 1 plus 1, which evaluates to 0. Fuck. Okay, so on that input, we have AB canceling with B, and we're shit out of luck. So to ameliorate this issue, if we pick a word that's a lower bound, then every other word, so let's say we pick B, every other word has some letter that doesn't appear in this word, and that letter will be 0, and so therefore the word that contains that letter will be 0, and therefore this will be the only word that evaluates to 1. So if instead we picked B as our word to evaluate to 1, and we go with A is equal to 0, B is equal to 1, B plus AB, 1 plus 0, it's 1. Cool. So we avoid the cancellation problem by insisting that our word has to be minimal or a lower bound within the context of its own sentence. That way, any other word that might cancel with it has some letter that isn't found in our minimal word, and that letter, we set it to 0, or we evaluate it in the case where that letter is 0, whatever. Thus, the resulting product of the letters, the word, evaluates to 0. Very important special case, if 1 is the lower bound, then the sentence will, of course, evaluate to 1 when all the inputs are 0. So, for instance, in 1 plus AB evaluated at A is equal to 0 and B is equal to 0, this is 1 plus 0 times 0, which is 1. Okay, cool. So, long story short, given any non-empty sentence, we can cook up some input to it where the sentence evaluates to 1, and we do that by finding a minimal word within the sentence and saying, we're going to use our normal indicator trick, cook up some input where just that word evaluates to 1 and all of the others evaluate to 0. Therefore, because there's some input where the sentence doesn't evaluate to 0, it is not the 0 sentence. We're done. So every non-empty sentence is not the 0 function. Therefore, if you have two different looking sentences, their sum is going to be a non-empty sentence, which is not the 0 function. So yeah, you get the purpose. It's kind of hard. Proof by contradiction is a little bit weird because it's kind of like, it's kind of like, if you're like doing a maze and you pick a random branch in the maze and then you figure out that it runs into a wall, and then you just go back and you say, okay, what was the last decision point? And so proof by contradiction is saying, okay, assume we take this decision point, we prove we run into a wall, therefore that was a bad decision. That's the idea. That's all I have to say. Thank you.